Okay, let's see what else we can accomplish with mole ratios here. They talk about consider the reaction of iron metal with oxygen gas, which produces iron 3 oxide. Okay, well, we need a balanced reaction before we do anything else. So iron metal is just Fe. Oxygen gas is diatomic, so it's not just O, it's O2. And iron 3 oxide, we need to do a little math to accomplish this. Iron 3 means we're talking about the plus 3 ions for iron. Oxide ions are minus 2s, so to balance this we have to go to 6. We'll need 2 iron atoms, that gets us plus 6, and we'll need 3 oxide ions, that'll get us a minus 6. Then we have equal amounts of positive and negative charge, which is what has to happen in an ionic compound. So Fe2O3 would be our product. And now we get to balance this. Tell you what, I'm going to do this kind of the wrong way just to show you what happens. And the wrong thing to do here is to start with the iron. It's not a huge mistake, but we'll do this and see what happens. We have 2 iron on the right and only 1 on the left, so we'll put a 2 on the iron. And now we go to our oxygen, and we have 2 and 3. Well, again, we have this lowest common multiple idea where we're thinking, okay, what's the smallest number I can make that using either 2's or 3's, and the answer is 6. So if I put a 3 there, I now have 6 oxygen on the left. And if I put a 2 here, I now have 2 times 3 is 6 oxygen on the right. So I just fixed the oxygen problem, but now I have 2 times 2, 4 iron on the right, and I have to go back and fix this number. So sometimes that happens that in the process of fixing one element, you will screw up another one and have to backtrack a little bit. So in this case, it probably would have been better to start with the oxygen. Then we wouldn't have had to make a correction here. We would have just immediately gotten 4 iron, hopped over here, put a 4, and that would have been it. So anyway, we got that balanced. Nothing too bad. And now they say, what if we had 2.2 moles of iron? How much oxygen would that involve? So they're giving us the amount of iron and asking about the amount of oxygen. So if we write a ratio for this, we'd say this reaction involves 4 iron for every 3 oxygen. And what they're actually using is 2.2 moles of iron. 2.2 moles of iron. And the question is how much oxygen? So X moles of oxygen. If you cross multiply this, you get 3 times 2.2, that's 6.6, divided by 4 is, oh boy, is it 1.65? Yeah, I think it's 1.65 moles. 1.65 moles of O2. Or, I'm trying to mix up the techniques here. If we put 2.2 moles of iron right here, and then we want to know how much oxygen there is, think about starting with 4, what do you do to obtain 3? And there are 2 answers to that. You could either multiply by 0.75. Okay, there are 3 answers to that. You could multiply by 0.75, or you could multiply by 3/4. Or, if you don't mind doing it in 2 steps, you could say 4 divided by 4 times 3. Those are all ways that you could take 4 and turn it into 3. Do any of those things to 2.2. If you do 2.2 times 0.75, or 2.2 times 3/4, or 2.2 divided by 4 times 3, all of those things will give you 1.65 for the moles of oxygen. So same result by a different path. Now, in B, they talk about, they give an amount of oxygen, but now they want us to find an amount of iron oxide. So our new ratio is not 4 to 3 anymore, it's 3 to 2. So if we do this with a proportion, we can say if 3 oxygens results in 2 iron oxides, then 55 oxygens, or 55 moles of oxygen, would produce how much iron oxide? You could cross multiply that. 2 times 55 is 110, divided by 3 is 3666, I think. 110 divided by 3. Yeah, calculator confirms X is 36.666666666 moles of iron oxide. Or, if you want to do the proportion thing, we have 55 moles of oxygen up here. Looking at the 3 and the 2, you have to think, what do I do to 3 to turn it into 2? And your answers are multiply it by 2/3, multiply it by 0. Lots of sixes, or divide it by 3 and then multiply it by 2. If you do any of those things to 55, the result will be, just like before, 36.66666. That's how many moles of iron oxide we get. Again, I don't recommend you try to learn all of these methods. Pick your favorite and just kind of ignore the others. You only have to be good at one of these because they all work fine. Oh, sorry, not new page. I have another page. There we are. Okay. Consider the reaction where hydrochloric acid or hydrogen chloride reacts with aluminum metal. Okay. So they say hydrogen chloride. Hydrogen's +1 and chlorine's -1, so that one's fairly simple. Reacts with aluminum metal, that's just Al, to produce aluminum chloride is made of +3 ions of aluminum and -1 ions of chlorine, so AlCl3. And hydrogen, which is a diatomic gas, don't forget your 2. So that's our reaction, and now we need to balance it. 1 hydrogen, 2 on the right, so we need to double this. Uh-oh. But now we have 2 chlorine on the left and 3 on the right, so apparently hydrogen was not a great place to start. Let's try that again. If we have 3 chlorine on the right, maybe we need to triple this, but now you see what's going to happen? Now we have 3 hydrogen on the right, on the left, and 2 on the right, and we still have a problem. In other words, we need the number here to be even because our hydrogens come 2 at a time, but it also has to be a multiple of 3, so you've seen this happen a couple of times when we have 2s and 3s that both have to go into something. The answer is to try a 6. What if we had 6 hydrogen chloride? Now we have 6 hydrogen on the left, so we need 6 on the right. Can do. And we have 6 chlorine on the left, so we need 6 chlorine on the right. Well, we could make that happen if we double aluminum chloride. And now that I've done that, I have 2 aluminum on the right, so I need 2 on the left, and there it goes. So sometimes you have to back up and change tack a couple of times before you finally get it, but we finally got it. And they say, what are they talking about here? They want us to make 4 moles of aluminum chloride, this, and they're asking how much hydrogen chloride, this. So if we made a ratio, we could say for every 6 HCl that you use, you will make 2 aluminum chloride. And then they ask, what if we use 4 moles, or what if we want 4 moles of aluminum chloride? 4 moles AlCl3. How much hydrogen chloride means we can say X moles of hydrogen chloride. If we cross multiply this, we're going to do 6 times 4, the opposite corners, that's 24, divided by 2, and that gets us 12 moles of HCl. Or, if you want to do the inline method here, we'd say we're starting with 4 moles of aluminum chloride. And we're trying to get over to HCl. Well, what do you do to 2 to turn it into 6? Times 3, of course. So take your 4 moles times 3. If this number is times 3, then this number is also times 3. 4 moles times 3 gives us 12 moles of HCl. Fair enough? Clean that up and see what B is about. If 65.2 moles of aluminum react, how much hydrogen will be produced? Okay, so we don't want this ratio anymore. Now they're talking about aluminum and hydrogen. So the ratio of aluminum to hydrogen is 2 to 3. We can say for every 2 aluminum, we're going to get 3 hydrogen. And then they say if we have 65.2 moles of aluminum, moles of aluminum, what does that mean? X moles of hydrogen. If you cross multiply that, it's 3 times 65.2 divided by 2, which I cannot do in my head. 97.8 it looks like. 97.8 moles of hydrogen. Or, if you want to do the n-line way, we'd put a 65.2 here. And now you have to think, starting at 2, what do I do to get to 3? And the answers are you could multiply by 1.5, or you could multiply by 3 over 2 if you're a fraction person, or you could divide by 2, turn this into a 1, and then triple it. So divided by 2 times 3 would also do the trick. And if you take 65.2 and then do any of these things to it, you will land on 97.8. Okay, one more. Consider the reaction between potassium sulfate and calcium chloride, probably a double replacement. Potassium is K+. Sulfate is a polyatomic. It's SO4 with a -2 charge. So putting those together, we get K2SO4. And then we have calcium is +2. And it's reacting with chlorine, or chlorides, which are -1, so we'll need 2 chlorines on a single calcium, CaCl2, to get our charges right. That's Ca for calcium, not Co for cobalt. Okay, so you remember how double replacements work. Either we think of it as the metals trading places or the non-metals trading places. Or the positive ions trading places or the negative ions trading places would be more appropriate here. If I swap the negative ions, I usually do the positives, but I'll do the negatives just to mix it up. We're going to get, need my space here. The SO4 will go over here, so we'll get Ca with SO4. More about the charges in a second. And the chlorine will come over here, so we'll get K with Cl. Calcium's charge is +2, sulfate's is -2, potassium's is +1, chlorine's is -1. So these products are lovely. They're very easy to balance. Here we just get CaSO4, no additional numbers required. And here we just get KCl. So that went nice. But it isn't balanced, so there's still more to do. Different color. We have 2 potassium on the left and only 1 on the right, so if we put a 2 there, that takes care of the K's. But now we have 2 Cl's. Oh, but that's okay. We already have 2 Cl on the left. We have a single calcium and a single calcium on the right, and we have a single sulfate and a single sulfate here. So Actually, this 2 is all it took to balance the whole thing. And all of these other coefficients are 1s. Okay, balanced reaction done. What now we can actually get into the mole ratios. They say 7.92 moles of potassium sulfate react. So let's see, this is potassium sulfate. They're starting there, and they want to know how much calcium sulfate is produced. Well, wonderful news. This is a 1-to-1 ratio, so with no math involved, 7.92 moles. Those numbers are always the same. This is like saying if there's 792 people in a room, how many heads are in that room? Those numbers normally match, so you don't have to calculate anything. You just know that they're going to be equal. I don't suppose they'll be that nice with B. Let's see what they ask for now. They say 0.56 moles of KCl. Here we are. Yeah, there's going to be a 2 involved this time. How many moles of calcium chloride are consumed? So the ratio now is 2-to-1. So we're talking about you'll get 2 KCl for every CaCl2, every 1 CaCl2 that you used. That's a 2-to-1 ratio here. And then they say, what if we have 0.56 moles of KCl? That will give us how many moles of calcium chloride? If you cross multiply that, you're doing 1 times 0.56 divided by 2, which will give you 0.28 moles of calcium chloride. Or, if you like the inline way, we have 0.56 moles of KCl. And looking at these coefficients, you'd say, starting at 2, what do I do to get to 1? And the answer is cut it in half or divide it by 2. So take 0.56 divided by 2, and look what happens. Same answer. Okay. There are, I believe, 3 more examples, and I'll do those in yet another video because I'm trying to keep these from getting too long. So see you in the next one if you decide to join us.